Okay, uh, almost on time. Hello, everyone. I'm Gianluca, and I'll introduce myself today because those are gone. Um, but yeah, I'm Gianluca. I'm one of the scientists at Wayve, and for the majority of the time I spent at Wayve, I've been thinking about world models. And today, what I want to do is kind of go through the journey I've been through when I started learning about world models and to where we are today. Um, so there's been quite a lot of talks from Jamie earlier today about how do we use world models, what kind of world models we build. So what I try to do here is, this is ultimately a tutorial, so I'll try to cover a little bit more about the literature about world models. So if you're interested in world model, you don't know what they are, that's probably a good starting point. If you're an expert about world model, maybe some of your work is in here, please give me a shout. And if I missed out on some work, still give me a shout. I'll buy you a beer, sorry about that. So quick agenda. Again, I'll start with a brief motivational, why I think world models are important, and then go through some of the what I would call standard techniques or techniques that have been widely applied to world modeling problems, and then dive deeper into like some specific work that I think is particularly interesting in world models for autonomous driving specifically. So again, as I said, disclaimer, the literature is huge. This is about 30-minute talk, so I couldn't cover it all, and probably I missed out on something. And if you have great pointers for me, I'll be very happy to learn more. So motivation, why do I think world models are a good idea? Again, I always start with this picture. You just look at this picture, can you tell what's happening? Like, do you have guesses? What's happening? What is the car on the left doing? Is it moving? Is it stopped? We don't know, but we have guesses, right? Then this is actually what happened is that car was stopped. We went around it, but there were multiple options there. And it was very clear to everyone in the room what these options were. And that's because everyone has an internal world model. We can access to that and we make decisions based on what we think is going to happen next. So, but where is this knowledge coming from? I think the interesting thing is like since the early, these humans start to like observe the environment. Then they learn how to interact with the environment, and they basically learn these samples and they build this world model. And this is not just this world model is built on any interaction and observation of the world, and we use it to generalize to so many different situations. Like many of us probably haven't crashed a car into a wall, but we all know it's not great, right? And we avoid that when we drive. So similarly, machine learning models can learn similar concept in a similar way, which is through observation, interaction, and mostly observation interaction with their own environment, or even observing other agents interact with the same environment or a different environment, etc., etc. And this can be done by observing videos, interacting with the simulator, observing other models interact with the real environment, and so on. So I think my motivation is like world models are part of the human intelligence and they should be part of any embodied intelligence. So I think that's why it's important to go through world modeling and understand where is this coming from, how it started, how it's going, and hopefully some of you have the answer of how this is gonna go in the future. So let's start with a brief introduction of world modeling techniques. So I would say these world models, this is a paper 2018. I call it how it started. In brackets, I would say with neural nets. World models started way before 2018, but I think this is one of the first papers I could find that approached world modeling using neural nets. And how does this work? So it starts with, if you look at the image on the top left, it's an autoencoder, right? So high dimensional observations of the world get compressed into a latent space and decoded back through reconstruction losses. Now we have a way of compressing high dimensional observation of the world into a very compact latent space through, in this case, was variational autoencoder. And what they did next here is to use the recurrent nets, because I would say in 2018 that was kind of standard way of modeling sequences and temporal. and especially like temporal sequences. And this paper started proving that you can learn both a word model and a policy through that schema at the bottom by interacting with the environment, and you can achieve state-of-the-art performance. So at the time, that was done using the OpenAI Gym environments, but they proved that forcing a model to reason about the environment and what happened next really helped learning a stronger policy. I think immediately after that, Dreamer V1 came out. That was 2019, and Dreamer V1 introduced this RSSM architecture, which is effectively a recurrent net with some fancy distributions being matched. I'm not going to delve too much into the details here. I put links to all the papers if you want to read about all the details. But I think what's really interesting in Dreamer, it was the idea that you can learn a word model and a reward model, which is observing the environment or even other agents interacting with the environment. And then you can train your own policy fully in imagination. So then when you start training your agent, there is no interaction with the environment. And they proved that by doing this, what you can do is learn a very strong policy. And again, at the time, they used continuous latency, so it was similar like a PAE type of encoder to represent these high-dimensional observations. And they proved using the DeepMind control suite that you can achieve very, very good results without even interacting with that environment, which is pretty important because when we think about embodying AI into a real robot that interacts in the real world, we can't just throw a robot out in the wild and allow it to make too many mistakes before it's a disaster, right? And so this was very inspirational at the time. Dreamer V1 was followed by Dreamer V2. I would say the main difference between the two models was they moved from continuous states to discrete states. And it was similar, so they learned behaviors fully in imagination from a word model that they could train from observations. And this time, this model achieved state-of-the-art performance on the Atari suite. So, right, so we see that we moved from one type of latency to another, and there is extended capability. And the Dreamer saga continues, and there is Dreamer V3, where in Dreamer V3, the authors start to propose a lot of tricks on how to train and stabilize the training of this recurrent net, which is not very easy to train. I don't know if you try to fit some Dreamer models, they're tricky. If you succeed at it, they do very well. And Dreamer V3, they show how by stabilizing the training and allowing to train and scale up these Dreamer models, they can start tackle much more difficult environments like Minecraft. So we started from very simple environment, DeepMind control suite, went to Atari, in the end Minecraft. So we kind of see this improvement in type of tasks that the word models can help to solve. So I'll pause here because I've mentioned a couple of times discrete latents, continuous latents, et cetera, et cetera. So like, if you don't know what these things are, it's just auto-encoding the images and videos. So there's some literature on how you can do that. So, and what's the goal here? The goal is to take a large representation or state of the word, like an image or a video, and compress it. Why we want to compress it? Because then the word model can treat this compressed representation, the reason in this compressed representation much better than it can do in the high dimensional representation. So I just put some pointers here, but I'm expecting everyone should be fairly familiar with these things. So we talked about recurrent nets, and we're moving now to transformers. So Fenaki came out in 2022. I mean, similar to what happened in language modeling, where we were modeling sequences, everyone moved from recurrent nets to transformers, and we kind of started to see the same shift happening in the word modeling world. So yeah, Fenaki came out, and it's like one of the first papers that proved that you can cast a word modeling problem, which is video modeling in the end, as an X token prediction or as a mask token prediction. Here is like an example of what Fenaki could generate. These are like rather small images They're quite basic, but also what they did is they started to introduce this concept that these word models can be prompted with text. So the idea is you have an encoder that allows you to discretize images and videos. Now you have a sequence of discrete tokens, and you can train your model to predict the next token or predict a mass sequence of this token. In this case, it was a mass sequence of your tokens. And when it's time to generate, you can just prompt your model to generate what you want. And I think this was kind of the first work that demonstrated that that's possible to do with transformers, video prompting, etc. Slight digression, Iris. So this paper introduced, again, similar ideas from the past, which are from Dreamer, but again, prove that transformers can be sample efficient word models. So they show that have higher sample efficiency than the corresponding like recurrent net models. And in very similar setting of Dreamer, they managed to like learn a policy completely in imagination, which it's very safe when you think about real world deployments. And they proved that on the Atari suite, they could do very, very well. So I think for now, we kind of jump back and forth from models that want to generate videos, models that want to learn a simulator of the world to train a policy. So what I'm trying to hint is word models can be used for several things. And you'll see like going forward, that's kind of the case. But yeah, so don't be confused by the fact that some word models are used to learn policies in simulation, some are not. So they've been widely employed in the last few years, and I'm trying to cover the most interesting work that I found so far. And of course, I mean, it hasn't been claimed as a word model, but this year we also saw Sora coming out as kind of impressive video generator. And with Sora, we started seeing the shift from transformer-based architecture, still transformer-based, but start to train these models using latent diffusion instead of next token prediction. And yeah, Sora, I mean, we all saw it, like realistic long video generation from text prompts. I would say this been done on unknown data sources, hasn't been disclosed, but it's probably large scale. And so we see this shift is when it went from recurrent networks to transformer to more diffusion-based techniques now. And last, I would like to mention, I know that the title of the talk is we're going to explore generative word models, but I would like also to mention that in the word modeling literature, there is an entire stream of non-generative methods. What does that mean? For example, this VJPA work from 2023 proposes a different idea where you cast the word modeling problem not as a I'm trying to predict what's next, which kind of takes away your ability to then generate samples, but you can still learn a representation that is word model live in a non-generative way. So I'll just mention it because it exists. It's not really the main topic of my talk, but I thought it was important to mention it. So this was kind of a very brief overview of how the word modeling framework shifted in the past like 4 or 5 years. And what happened is word models started to be widespread in autonomous driving. So here I just put a couple of images from a couple of review papers that came out recently that discuss about how word models are being used in autonomous driving. And actually, yes, everything here, if you look at these images, everything seems to start about 2022. Well, there's not much being reported earlier, but I would say that before 2022, at Wayve, we were like already investing and thinking about word models. I would say very early on, about like 2018, at Wayve, we published the blog where we managed to train a policy and deploy it in a small car. Too easy, I don't know if you're familiar with it. Learning the policy fully in imagination on a word model that would fit on real world data. And then we started investing more and more, where we started publishing papers about predicting the future, starting to train these word models, first starting from simple representation like predicting the future in semantic segmentation space, moving to like fiery, that did it like in bird's eye view space. I know, and some of this work then started to get, and we try to like kind of close the loop with what I've presented in the literature before, where in 2022 at Wayve we published MILE. So MILE is a recurrent state model, very, very similar to Dreamer, that predicts bird's eye view segmentation and action. So this is effectively a model that has learned jointly a word model and a policy. We deployed this in Carla, and at the time, I think we got state-of-the-art results. Of course, things are gotten much, much better now. And similarly, at the same time, there was this work called SAM2, which is very, very similar to mine. I just wanted to mention it because I think the two works came out basically 1 week apart. We didn't know. They didn't know. We just found it. And we just found it. So that's another example where using these recurrent state models in Carla, people were able to fit word models and a policy jointly. Right, so then we moved on from that, and the main reason is we tried to scale that up to real-world applications, and we didn't really see the scaling curve that we wanted to do, so we decided to rethink what we were doing, and that's how we started working on Gaia. So Gaia is our way of rethinking scaling word models with data and compute. And so what's Gaia? Gaia is a word model based on an autoregressive transformer, and Gaia employs a lot of different modality encoders to compress images, actions, and text as a set of tokens. Once you do that, you can just take this multimodal sequence, align it temporally, and just model this as a sequence. So we did this last year. We presented it at, I think, a CVPR last year, and I think it's in most of our talks. Today, we are now using it in conjunction with Prism, like for several things away. Yeah, what was impressive when we first saw is like we started seeing that these new word models that we were training started to have a lot of nice things that we wanted to see in word model. They started to show us that they are intelligent, they do understand the word, and this is one of the examples, right? They started to demonstrate us that they do understand multiple options. And so if you can take a word model, you can initialize it with sequence and start unrolling. And if you take a few samples, you'll see that there is quite a lot of diversity. And this example, I think it was in Jamie's talk as well, but again, it's one of my favorites because here is just the word model is demonstrating that they can understand that even the interactions with other agents can be different. There are like multiple options out there. And having all this information is really, really important when it comes to like make decisions for driving. And here, I mean, you can see that these video generations are not like pixel perfect, but the concepts and things that are really, really important that we should care about are there. And that was really remarkable when we first saw it. We were so excited. Again, I think this has been shown today again, but another mind-blowing moment for the team. It was when we first saw these results. We could force a ego vehicle to drift in the wrong lane, and Gaia could simulate other vehicles responding to our actions. Again, all of this is fully end-to-end. Nothing is scripted, and it's just an emergent behavior that you get from training at scale. Again, we allowed Gaia to generate from text prompts, and here's some example where we just say I want the weather to be sunny, rainy, foggy, snowy, and we can get very, very realistic samples out of it. Similarly, we can control for the time of day, and all the samples look realistic and respect the prompts. And I would say one other important thing here is like the long generation. This is just 2x speed. There is a 2x speed up in this video, but here we just started generating a video and stop. We kept going. This goes for like minutes in the future, and it was one of the first times that by looking into the word modeling literature, I could find something that is that stable for that long in terms of generation. So that was about like a year ago. So after that, we started seeing a lot more work coming out in word modeling for autonomous driving. this is just one of these examples, and we started seeing that there's been a little bit of a shift towards like latent diffusion. So Drive Dreamer is one of these examples. So Drive Dreamer is like a latent diffusion model that allows to generate videos from HD maps, 3D boxes, or actions. And you can also predict future actions. So once you can do that, you can look back your next action into your world model and enroll from there. And this has been trained on like and evaluated on new scenes. And here are just some examples of what they can generate condition on like a 3D scene. And yeah, it's truly remarkable to see that so many different techniques can be just trained with data to understand the world. It's just kind of a proof that the intelligence and all the concepts from the world that you want to learn can be learned just from data. Here's another example where they show how once you put back the action that you predicted into the world model, you can drive within your own imagination. So what they show at the bottom is the velocity and the steering angle predicted by the model, and at the top is the video predicted by their own world. So they can basically learn to drive in imagination after that. Similarly here, like Drive World model, another latent diffusion model. The main contribution here and difference, like we started, like all the videos I showed up to now, they're like single camera, right? When we think about deploying autonomous driving to the real world, all these deployments do have multiple cameras. 6, 7, 8, 9 multiple sensors, and they are very high dimension. So Drive World model, I think, is one of the first models that came out that started demonstrating that this can be done with multiple cameras. The geometry across the whole cameras is fairly consistent with no prior geometry into the model. And also this model could also generate actions and was trained on new scenes. And the caveat here is you can see that these videos are a little bit jittery, and that's because once you start adding cameras, you can't simulate at a very high frequency. It's very expensive. And so this model runs at a frequency that is lower than all the models that I showed before, but they extended it to 6 cameras, which is really impressive. And again, if you look at these images and pay attention to like the consistency, it's quite remarkable. Right, and then a driver I came out. So interesting here, we started to see multimodal language models being added on top of word models. I think this is one of the first I've seen, and it was trained on new scene and some private data sets that have been disclosed, but the video generation here is conditioned on actions, and these actions are described by text. And there is a large language model involved into the generation. I thought it was quite a novel idea. We've never seen that before. But anyway, we started to see like diffusion and multimodal language models coming together in the word modeling world. And moving on from real world images, there's been quite a lot of work as well trying to do word modeling in a different space, which is this case for off-word is 3D occupancy. And here, an interesting thing is like what we started to see is like moving from like plane transformers similar to like VITs or standard transformer to like spatiotemporal transformers, right? Because when we think about the world and the word model, both space and time are important. While up until ST transformers, most of this work have model space and time as a unique thing, and that's more expensive. So Awkward started to do this using 3D occupancy maps. And I think after that, Wabi published Copilot 4D. And still, this is the discrete diffusion model. The observation space is like LiDAR space. I think it was trained on new scenes, Kitty and Argover, so like more data sets, LiDAR point clouds, like a different like observation space. But again, all is the same ideas of trying to model the world and in a certain representation space and try to predict what happens next. And here's a like great example from examples from their blog where they enroll time and they show how they can predict lighter point clouds in different scenarios. And this prediction is quite accurate, and like for a few seconds in the future, which is probably what you need for like plan. Finally, I think this was mentioned by someone else today, like very recent paper. I think it came out like a couple of weeks ago, and we started to see like more diffusion models coming into the world of word modeling and started to tackle high resolution video generation. So this model Vista is quite impressive video generation at a very high resolution. So this is the highest resolution I've found in the literature. And these are some example videos from their work, quite stable generation. And finally, also this one came out a week ago that I think the most interesting thing about this paper, it was starting, yes, they do propose a new generative model to generate videos. But the most interesting part here is they just don't limit themselves at showing that they have a new word model that can generate realistic samples. They try to close the loop. And closing the loop means they show results where if you analyze your failure patterns on your end-to-end policy, and you have a way of generating new data samples that tackle those failure cases, you can actually improve the performance of an end-to-end policy. The interesting result here was they demonstrate that you need both. You need a really good word generative model and a really good strategy to identify and generate the samples that are which you are weak. And have a look at the paper, but yeah, the results are pretty clear. You can't just take a great word model, generative model, and generate random samples, throw them back into your training set. That's actually degrading your performance. And at the same time, you can't generate samples of things you fail at from a non-generative model that is not good. Once you have both, you start to see the improvement. So I am almost at time. So yeah, let me just wrap up what I tried to discuss today. Yeah, I tried to stay away from like just Wayve specific things. I wanted to like kind of try to cover a little bit what's out there because word models are starting to be out there, especially like in autonomous driving. We're starting to see more and more companies or research labs starting to investigate word models and invest a lot of them. So what do we have seen today here? I would say, yeah, we should probably, I hope everyone agrees that now word models play right now an important role in embodied AI and will play a massive role. So it is important to invest in them. And we've seen, I would say, 4 main techniques that are commonly applied in the word model, like something like Dreamer and recurrent models. We started to see like vector quantized representation that can take large spaces like images or videos and compress them into like token spaces. Started to see diffusion models, and we also briefly seen JPA models, which are these non-generative models to learn models of the word. And we've seen that all these techniques can get put into work for autonomous driving. And they can employ as data generators. They can employ to understand the word as representation learning tasks. They can be coupled with behavioral learning. They can be used for occupancy prediction and further planning. So applications of word models in autonomous driving are widespread. And so, yeah, I would just like to leave everyone with just one question, which is, how do we improve them? How do we leverage them to unlock the full potential of embodied AI? And that's just an open question I'll leave to the room. Thank you very much. And I'm happy to take questions.
Thank you, Gianluca, for the great talk. Yep.
You mentioned consistency, frame over frame, and also multi-cam. And then you also showed, I think maybe one of the Gaia videos, and you said you let it go for a minute. Do you have an idea of how large scale consistent it is? There you go. Then second for that, I forget if it's the Prism or Lingo scripted model. How aware of large scale the first way to tell you guys that my back in place and right.
Okay, I'll repeat the question for online. It's mainly two questions here, and it's correct. So one is if we have a sense when we generate from Gaia for like minutes, whether we look back to the same place. And the second question is for other models like Lingo, does Lingo understand we went back to the same place and can tell us that? So to answer the first question is like, no, we've never seen really like looping back to the same, exactly the same place. And the reason is Gaia is effectively a transformer model. You just sample the next token. So in order to go back to exactly the same place, the way we model one single time step is like thousands of tokens. So unless you sample exactly the same thousands of tokens, we are not at the same place. The combinatorial space is exponential, and so usually we never seen Gaia going back to the same place. We have seen early on when we were experimenting with it, Gaia trying not to be very inventive and mostly like try to remember some places of the world that we have seen more than others. But we immediately started seeing that when we start scaling this up, that goes away. So he stops memorizing. And the reason is, or at least my understanding of this is, when you expose these models to significant amount of data, they can't memorize them anymore, right? So, and neural networks are extremely lazy objects. So the easiest way of solving that is not memorizing what you've seen, but is really synthesizing and like condensing the rules of the word that generated the data. And now they become amazing data generators. And so we stopped seeing this memorization and going back to the same place kind of behavior. Regarding Lingo, I have to be honest, I don't know. I don't know if we have an example of going back to the same place and Lingo saying we just go back to the same place. But in general, like all these models have fairly limited memory. So even going around the same, like one block and back, probably takes minutes. So it's very unlikely that these models, until they start fully generalizing to extremely long contexts, will be able to do so.
Right? So, like generalizing, for example, like driving in reverse.
The question is if we try to see how well Gaia generalizes while trying to drive in reverse. And yeah, the answer is yes. Yes, we try to like drive in reverse, and because it hasn't been trained on a lot of data where we reverse, what it does, well, we have two samples. Interestingly, in one sample, we started reversing and Gaia did a U-turn, because that's how you start the U-turn. And in the other one, it stopped reversing and it started to go forward. But yeah, I think we never showed it publicly, but like we kind of stress test Gaia a lot more. To the point that at the time of publishing the paper, what we did is we took one image of everyone that worked on this project's hometown, wrote in their hometown, and we started enrolling from there. So what we saw is it was mostly trained on UK data. So when we initialized it on right-hand driving, what Gaia usually did is went up to the left and kept driving. But yeah, he generalized it. It generalized quite well. Of course, the image generation wasn't the same quality of the data we trained on, but like the concepts and even the behavior of I initialized this model on the wrong side of the road according to this model, and this model decided to go back to the right. I was kind of impressed. We didn't expect it, but started seeing all of these emergent behaviors.
During the sampling of the filter in the Gaia model, we are choosing from multiple possible filters. This includes the behavior of other agents, like if one vehicle is cutting you or not, or yielding you. I was wondering if we have more deterministic control over the behavior of other agents during the sampling of our model.
So the question is, when we sample feature from Gaia, and the feature is multimodal, we do not control other agents' behavior. And so the question is there a way of controlling, having more control? Yeah, actually, yes, there is. I think I haven't included in this presentation because I tried to limit my tutorial presentation to paper that we published. But I think today Jamie gave a sneak peek of how we can do that with Gaia, which is, for example, the examples that we gave on Prism, like we can add agents there and control what they do in a video. And so, yes, we do have new versions of Gaia where we're working on full controllability of other agents through their 3D position, text, etc., etc. So it's something that we have in the works, but we're adding the ability to control better the behavior of other agents.
On the back.
What are your thoughts on training a controller based on the latent representation inside of the Gaia model?
Question is whether thoughts on training a controller or a driving policy, imagining the latent space. Yeah, that's definitely like interesting thought. I mean, a lot of these papers that we've seen have done that, so I don't think it's not plausible.
One last question.
You mentioned that the RSSM and MILE didn't scale data you then work on Gaia. Can you mention what about RSSM didn't scale? Was it for computational efficiency of it, or what?
Right. The question is, I mentioned that when we tried to work on RSSMs, we didn't see scaling with data and compute. And what's your reason for that? So I believe that the main reason is like RSSM used to be trained with this idea of you have a prior distribution of what's going to happen next and a posterior distribution. So, and then you match those with a KL divergence. So when you looked at the whole optimization landscape, you had like your reconstruction loss, two moving distributions, and a KL loss, which if you don't tune correctly, collapses. So what we've seen is it wasn't as easy to just say, okay, let's double the parameters, let's double the data. You start training, everything seems fine, but if you end up in that weird space of your optimization where that those two distributions collapse on top of each other, the prior and the posterior, you're doomed. You forget everything. And we've seen that with scaling, we couldn't really control that easily. So it was really hard to tune all those hyperparameters. Whilst when we switched to Gaia, we reframed the whole problem as that's just next token prediction. And so there's only one loss, it's the cross entropy loss. And you're guaranteed that lower is better. Right. So in the RSSM formulation, you don't have that guarantee because what is better, like lower KL, better reconstruction, you have to trade one off for the other. So it made it very, very hard to scale just because you start an experiment, you start training well, and after a couple of days, it collapses on you. And then you're like, okay, let's start from scratch, change your hyperparameters and go back and forth. While with Gaia, what we saw is that double the parameters, scale a little bit the learning rate, go. And you see that loss keeps going. And if you don't stop, it keeps going. Right. So I think that's what allows us to really scale.
All right. Let's thank again Gianluca for the amazing talk.